Okay, shall we start? ザフィラさん、can you start first?
はい。Can you see my screen, 先生 Hello? Hello?
Hello?
Can you hear me?
I cannot hear your voice.
Hello? Hello?
I cannot hear.
Hello?
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 Okay, okay.
Okay. Can you
Can you
see
see my
screen,
screen,
sensei?
Sensei?
Yeah, yeah.
So, thank you
Thank you
so
so much
for
for
adding
adding
the
the
new
new
stiffness
stiffness
for
for
viscoelastic.
viscoelastic.
So,
So I already run the analysis
for
for
viscoelastic
viscoelastic
and
and
including metallic
metallic
temper.
temper.
So basically
The
system
system
looks
looks
like
like
this.
this.
We
We
have
have
viscoelastic
viscoelastic
and
and
then
then
metallic
metallic
temper
temper
as
as a
like a
like a
fuse, and then
fuse
connected by
connected by
steel
steel
beam
beam
to the
to the
wall.
wall.
Okay.
Okay.
And
And
then
then
this
this
is
is
a
a
spring system, basically
basically
viscoelastic in
viscoelastic
parallel and
parallel
series
and
to
series
metallic
to
temper.
metallic temper.
And
And
here
here
we
we
have
have
the
the system
with
with the support beam.
And
And
then
then
here
here
is
is
the
the
hysteresis
hysteresis
graph
graph
for each element.
element.
So first we
So
have
first we have
viscoelastic,
viscoelastic,
and then we have
and then we have
metallic
metallic
temper,
temper,
including the support beam.
support beam.
And then we have
And
to
then we
connect
have to connect with
our
the
couple wall
upper
system.
wall system.
And finally we can
And
get
finally we
this
can
total
get this
system
total system
for hysteresis
for
graph.
hysteresis graph.
And then here
And then
I
here
calculate
I
for the
calculate for the
viscoelastic. So this
this
properties based on
properties based on
Christopher's book.
Christopher's book.
So I
So
choose
I choose
they have a
they
few
have
type
a
of
few
material
type of
ABC,
material
and
ABC,
I
and
choose C type because
E type
it have
because
higher
it have
stiffness.
higher
If you can
stiffness.
see
If
the
you can see
GE is
the
higher
GE is
compared to
higher compared to
C.
C.
And here
And here
from here I can
here I
calculate the
can calculate the
properties,
properties,
and
and here I
here I recalculate them.
recalculate them.
And the main
And the main
point that we have
point that we
to
have
get
to get
input in
to input in
sterility is
sterility
the
is the
stiffness A and the
viscous
C.
for C.
And to
And to control this,
how
how
force
much
that we can
force that
control
we
is
can
by
control
the
is by the thickness of the
viscoelastic material.
material.
And from
And from
here,
here,
we can
we
use
can
this
use this
formula
formula
to
to
form the
form the
hysteresis
hysteresis
graph.
graph.
So
So
you
you
can see
can see
100%
100%
the blue line
line
at 400
at 400
kilonewtons
kilonewtons
with displacement
with displacement
60 millimeter.
60 millimeter.
And when
And when
the force
the
reduce
force reduce
and
and
the displacement,
the force also
the
reduce.
percentage
The
reduce with
percentage reduce with
the force also
the force
reduce.
also reduce.
This is for
This for
viscoelastic
viscoelastic
temper,
temper,
and
and
this one
this one
for
for
metallic
metallic
temper.
temper.
Similar
Similar
design
design
as
as
my
my
master
master
thesis.
thesis,
And this is the
the
hysteresis graph
hysteresis
by
curve
Dini
by Denis
Hysteresis.
Cherkov.
And
And
I
I
put
put
500
500
for
for
100%.
100%.
So
So
when
when
the
the
viscoelastic
viscoelastic
deform
deform more than 400,
the metallic
the
temper will
metallic temper will
deform at
deform
the
at
second
the second
stiffness at
stiffness
500
at 500
kilonewton.
kilonewton.
And this
And
is
this is
viscoelastic,
viscoelastic, the
the
damper with
support
the
beam.
support beam.
So I
So
calculate
I calculate this is from I
got from
got
Stera
from
3D,
Stera 3D,
and from here I can
and from
identify the
identify the
stiffness for
stiffness
the
for the
both beam,
pulse beam,
and then
and then we can
multiply
multiply
with
with
viscoelastic and
viscoelastic and
metallic
metallic
temper.
temper.
So
So
this is
this is
the
the
hysteresis
hysteresis
graph
graph
for the
for the three
elements.
elements.
Okay.
And
And then here,
from
from this only couple wall, so in Stera 3D, I only push
the
the
drift
drift and for the couple wall only without any beam or damper. So here the capacity curve, and I can get the stiffness from here.
And from
And from the stiffness, I can add into the system. And this is the overall hysteresis system.
Okay, and
Okay,
then
and then
for the analysis, so I use as the procedure that we discussed before, basically from 100% story drift, and then we can get the cyclic drift for 1 over 2.
One moment.
Yes, yes.
Could you slide 8?
Slide 8.
Slide 8.
Yes.
Yes.
Yeah. So you combine viscoelastic, metallic, and support.
Yes.
And is this a result of Stera 3D?
No, this one, the support is from Stera 3D,
Sensei.
MY.
Well, but how about the metallic?
Metallic is this one is by calculation from this course.
If you combine all of them, it looks oval shape.
Because of
from here. This one.
Yeah. If you include the metallic, it must be upper limit. I mean, bilinear. That's
bilinear like this. Bilinear hysteresis, like this one.
Yeah.
It's not look like this, Sensei. Like
you can see.
It's an oval.
I don't understand. You combine in series, right?
Yes,
Sensei.
Plastic, metallic, and support you combine in series.
Yes.
So it means the force is common for all of them.
I see.
The force have the upper limit because of metallic. But it looks force could be more than 1,000. Why? Metallic damper cannot support such big shear force.
Okay.
Okay, I will do correction for this one, Sensei. And how about the overall system?
Why you do pushover without damper?
I just want to get the stiffness of the building only.
Why?
On Kakawa, because to get the stiffness of the structure.
But you have a metallic and also viscoelastic damper has a stiffness.
Yes, but I added together like this. So this is the combine, the metallic and the support. And then after that, I only run for get the stiffness from the couple wall. And after that, I combine everything together.
What do you mean combine?
Damper and system. When we combine damper and the couple wall, the stiffness increase, right, Sensei? So
sorry, I don't understand. How you can combine?
My plan is to form the total graph for all the elements. So can I just add all the stiffness together and form the hysteresis curve like this? Is it a wrong method, Sensei?
Zakura-san, if you have two stiffness in couple, you can add. But if you combine two stiffness in series, you cannot add.
Okay.
If this stiffness is K1, if this stiffness K2, the total stiffness is
K1 plus K2?
No. It is something like this. K1 plus K2.
Okay, Sensei. I will do correction.
And then this one, Sensei, I run in the Stera 3D. with displacement design method. So
what do you do without?
this one without damper, but this one means that 0% of damper, but this one is start from 10% to 100%.
But what do you mean 10%? Are you talking about viscoelastic or a battery? Which one?
Both of them, Sensei.
Both 10%.
Yes. Yes.
How did you decide, combination of viscoelastic and battery?
From here. So from here, we start from 400 kilonewton, and then we can get K and C. And then for metallic is 500. Start from 500 here. Required shear capacity is 500, and then this 100 to 10%. And from here we can get K, the stiffness. And
so, could you go back?
Yes.
So, if 100% viscoelastic, you combine with 100% metallic.
Yes, Sensei.
Why?
Why? To make sure the capacity reduce by percent same. Because the main damper will be viscoelastic, right, Sensei? So, for example, here the viscoelastic perform at 400 kilonewton, and metallic.
Could you go back one slide? How much omega?
Viscoelastic here. This one.
Yeah. How did you decide?
This is given the loss factor here, Sensei. So for this method is 0.9, and this formula, and from here we can get the conclusive function W here.
Sorry, I don't understand. What is the meaning of this loss function?
This one. Sorry, you mean this in this first formula? This is the period of the building.
Period of the building?
No, sorry. Circular frequency, from the period of building, we can calculate the circular frequency.
So omega equal 1.
Yes.
Period is 2 pi divided by omega.
Yes.
So your building is almost 6 seconds. Natural period. Are you sure?
No. That's effective period 0.9. Yes.
But you
this
is 0.9.
No. This one, Sensei, is from here.
So what is the meaning of this formula?
This is loss factor. I can understand this is the loss factor for these properties.
I don't understand. What is the loss factor? This is a test conducted in this book.
Yes, Sensei. So
if you test this material with different, you will get different eta.
Okay.
You cannot use this eta for your case because omega is different.
So I just have to replace this omega, and then I can get different loss factor.
Yeah, those factor may change depending on the frequency.
Okay. I will do correction for this one.
Nothing.
その損失係数は電弾性ダンパーの最大力と先端合成の比率です。
オメガって何だよ。
オメガ、年弾性ダンパーなので、結局速度、その速度を出すがオメガから最も、先生がおっしゃったように、オメガが変わると、その年性要素の減衰力が変わるので、
うん。損失ケースも変わるってことでしょ？
はい、変わります。
だからこれはこの実験で使ったオメガの時の損失ケースなんて。
その実験で、それは多分、なんていうんですか、係数で求めたら多分 0.90 に。
0.90 ってわけじゃないんだよ。
減衰力、楕円形があって、減衰力が上がると、速度が上がると減衰力が上がるじゃないですか。
うん。
でそれに伴って瞬間合成も上がりますよね。
うん。
なんで結局多分比率は一緒になると思うんですけど。
GE と GC って係数なんじゃないの？違うの？
それは実験、これはわかんないですけど、実験結果です。一般的に。
ちょっとよくわかんないな。ミーターが常に0.9って仮定していいのかね？振動数によらず。Is it okay to assume constant ether?
Yes.
Yes.
Why?
Because I want to use these properties. Like
This is a test in this case.
yeah. But the constant is GE and GC, right, Sensei?
Yeah, so if you change omega, you will have ether. This is it's not constant, right? It's a function of omega.
Yes,
Sensei.
So why you can use the same 0.9?
Okay, I understand.
So this eta is for 3.5 Hz frequency. So if my building have different time period, so my omega also different, and my eta also will be different.
And you input K and C from GE and GC.
Yes, Sensei.
Right? So K and C has nothing to do with omega. So stellar input doesn't change, right?
Yes.
So maybe this C and K
This depends on the area and the thickness of the
viscoelastic material.
Is this factor is related to C and K? K and C? I mean, this ether.
So this one. And then
no, Sensei. Only the K is depends on GE and the
thickness and the area
of the shear.
How about C?
C. Oh, yes, C.
But C is omega.
Yes, Sensei.
How about C? GC?
GC? This one?
No, this is GCW. Omega.
GCW omega.
Here. I just want to check GC.
If omega constant, then GC will be changed, right, Sensei? Because omega for one building is constant.
Yeah, it looks, GC is this one divided by omega.
GC equal to eta times GE over omega.
Yeah.
So if GC is constant, our eta will be changed. The loss factor will change.
잠깐만요. Click this one again. Click. And this is K3 O3 divided by P3 and omega. Yeah. Okay. Yeah, so putting GC here. No, 違うか。JC じゃない。BC、いや。まあでも、オメガによる、okay. So anyway, you are dividing by omega. So this value is doesn't change if you use another omega. These two values doesn't change. Nothing to do with omega, right? But eta 3, if you use this 3.5 hertz, you will get this value. Mm-hmm. But if you use value, you will have another eta.
Okay, sensei.
But this value may not change.
Okay.
So my question is, this 400 is the maximum shear force, maximum force of viscoelastic, if frequency is 3.5 hertz.
Okay.
So if you use this viscoelastic for your coupling wall, maybe maximum shear force is not this one. So your building is
0.04 zeta.
How much? 9 hertz, right? So you can estimate this one. Will be
let me try.
In case of 9. I don't know if it is okay to put this.
Okay. I will do corrections. I will listen to you.
And also, so you have a viscoelastic damper.
Yes.
Okay. And this is a shear force of viscoelastic damper. And then you put metallic damper here. Okay. So metallic damper, for example, you design to yield at Q. Okay. So if QC is more than QY, the total shear force. So if in this elastic range, it is something like this, oval shape, because of a viscoelastic. But if it is over QY, I believe this hysteresis will be something like this. I mean, it cannot be over.
Okay, sensei.
So this part will be, over QY. So it cannot be reached, this value.
Okay.
Because metallic damper here there.
Okay, sensei, I understand.
You understand?
Yes. I will find the formula for that hysteresis, sensei. Because this one is just plus minus to get this one.
And did you calculate the response of coupled wall with
response?
Yeah.
You mean
this one?
dampers?
Yes,
Sensei.
So this without damper?
No, I'm asking about the time history analysis.
Yes,
This one.
No, could you draw hysteresis of
hysteresis
with
the can I open one of the
Okay, ouch. So less than 50%.
hysteresis of the damper,
Damper, sensei. So viscoelastic is this one.
It looks like you haven't set up any confidence.
And then this one is
this
it's supposed
to be viscoelastic.
Oh, sorry,
sensei. This is the support beam.
support means?
Sorry. This one, B1 is the this one.
So force is very big, 3,000, almost 4,000. Okay, more than 4,000. 本当かな増えたくなるな。Something wrong. 4,000 kilonewton. Okay, how about metallic damper? Same beam.
This is metallic.
Only 0.2. Why shear force is so small?
Is it because of the force is taken by the viscoelastic?
なんか変だな。Viscoelastic shear force is so large, but metallic damper is shear force is so small. Force must be common for two elements.
But the capacity is different for viscoelastic.
Viscoid.
You combine in series, right?
Yes.
So the force is common for two elements. You understand? So this is viscoelastic, this is metallic. So if you apply F force, this force is also F because the series. This is also F. And the other side is F. and the force is also F. Any section, shear force is the same for all members connected in series. So force is common.
Okay.
So force must be same as this one. Cannot be larger. But in case of viscoelastic, your force is so large, and the maximum value is 4,000. Why?
I don't know. I have to recheck.
Would you send me this file to me?
Okay, sensei. Okay, sensei.
Something wrong.
But I have one question, sensei. If Sarah have problem, is why time history analysis looks fine?
It looks fine, but something wrong.
Okay, sensei. Right. Okay, that's all, sensei.
So please make some theory how to combine viscoelastic and metallic.
Okay, sensei.
So you said metallic damper is a kind of fuse.
Yes.
Right? So
okay. What I understand is when the viscoelastic, the force is more than viscoelastic capacity, then the metallic will deform.
Sorry, I don't understand.
The main damper in the system is viscoelastic. So, for example, we designed the maximum capacity is 400 kilonewtons, and when the force is larger than 400 kilonewtons, then the metallic damper will deform to execute the extra force.
Could you write some PowerPoint to explain this? Well, hand drawing is okay.
So for example, we designed this for 400 kilonewton. So if the earthquake that the edge of force the force here is more than 400, for example, 500 kilonewton, then this metallic damper will start to deform to avoid damage to the car support and the wall.
So sorry, could you explain how much capacity of metallic damper?
It starts from 500. Here.
Earthquake is 500.
Not the earthquake. It's 400. The force. It's force. The force that we designed for the yielding force. Yes.
Okay.
So for example, 400 here, but for the metallic, it will start yielding.
Sorry, could you repeat again?
Okay. So for the viscoelastic is 400, maximum is 400. And if the axial force is more than 400, the metallic damper will deform, start to deform and dissipate energy.
No, both damper will deform
together. But
of course it's together.
But this one, the larger deformation in the second stiffness will be deformed larger after 500 kilonewton, right, sensei?
Yeah, of course.
Yeah.
Of course.
So the metallic damper will activate after when larger earthquake come. So that
you design combine viscoelastic and metallic.
We can get the stiffness and input in there. So for the metallic damper, the maximum capacity it can attain is about 800, about 900 kilonewtons. That is the maximum capacity. So we must make sure that the force is earthquake can be adapted less than this one.
Earthquake. Um, What is the capacity of supporting beam?
Supporting beam.
It should be more than the metallic damper.
Area of the supporting beam.
So here is the size. 700 by 350.
And from
Strat
Strat
3D, I get the my is equal to
here,
this one.
One moment. Sorry, how do you get the capacity of supporting beam?
From
How did you get this MY?
my is for maximum data beam, I think. From here.
Can you see my screen?
I can see PowerPoint.
Okay. Here.
This
is from data beam.
Data beam. Okay. And yielding moment. But you must calculate shear force.
Shear force.
Can we
calculate from here?
You have a beam, right? And there's a coupling wall, both sides.
Yes.
This is a wall. And this is beam. Right?
Yes.
And if you apply earthquake, you will get moment. I don't know. For example, well, if you assume symmetry, this is the moment. So same, right? And both end, this is the maximum moment. And this is MY. And this is, I don't know, I cannot see how much, but in this case, my question is how much shear force of this supporting beam, of this beam?
Last size was 400,
almost 400
kilonewton.
But the last time you put the concrete beam.
No, steel beam.
Huh?
Steel beam. We use steel beam since. Yes.
How did you calculate 400?
Actually,
we have this model. This one. From here.
From here.
And then.
think last time we discussed this one. Yeah,
So we
get
get
my,
my,
and then we can
calculate the shear force.
calculate. It's almost 300.
How did you calculate QM?
QM equal to
Could you click? No,
here.
here.
Here is
Here is
from
from
stereotype
stereotype
distancing.
no, I know MY. So I'm asking how do you calculate
QM.
so far? QM. Could you click next one? Yeah. What is the meaning of this?
Should
Should be
QM
equals to moment
divided by 2L.
by 2L.
No. Moment divided by 2L?
Yes.
No. 2M divided by L. Or moment divided by L divided by 2.
Equal to the shear force.
So, moment is, for example, in case of counter, if you apply Q, this M is Q multiply L. So this is a basic of structure mechanics. Moment force caused by lateral force. I mean straight force. Force multiplies is moment. You understand?
Yes, I see.
So in your case, point is like this shape. So half length of beam. It's like cantilever, right? This is shear force Q, and this is M.
Yes.
So you can get Q equal M divided by half of L. It's a basic of structure mechanics.
Okay.
Yeah, so your beam is yielded by My. And at that time, shear force is this 300, I cannot see.
320.
No, could you put, click, 387, about 400. Yeah. So this is a source of supporting beam. So metallic damper must be weaker than this one. Otherwise, the supporting beam will have damage by fracture. Yeah, so this is a beam with a damper. Okay, and this will damage flexural yielding by My. At that time, shear force is 387. Okay, so this is a coupling beam with damper. Then you put the metallic damper in the middle. You design metallic damper by bilinear, yielding by Qy. But Qy must be less than 387. because you want to dissipate energy at the metallic damper. So Qy, I don't know, 100% is you assume 400?
Yes.
Actually, 400 is even larger than this one. Okay, well, 400. And you are seeing. Then you are talking about viscous damper here. But the viscous damper, this hysteresis, this QC, depending on the velocity or frequency. Frequency is high, it will be getting very large, very large. So if this is over than 387, the supporting beam will make damage. So this is a problem, right?
Yes.
Yeah.
So you want to combine metallic damper here. Because metallic damper has a upper, yielding by Qy. So it means viscous damper also go over Qy. So hysteresis will be something like this. Oh, sorry. So, but from your stereo result, I don't know why, but it is increasing very much. I don't know why it's so huge value here.
Since I have one question. So M is equal to 1 to 400, right? And divide by half of the length of the beam. The beam length is 5 meters, so equal to 250 centimeter. So
when we divide by
M is equal to be 496 kilonewton instead.
Could you click here again? So how did you get this 320 here?
Actually, Sensei, you're the one put this one.
This Excel file is from
you, Sensei.
Maybe at that time coupling beam is 640.
I see.
But you must
Okay.
change this value.
So this one should be.
Yeah.
Okay.
But here our MY is different.
MY is this one.
This is a length of what? Coupling beam? L.
This only the support, Sensei.
Only the support.
The support
beam.
The support beam. But how did you get this one? Right here.
One from
here.
Data beam.
But do you know how?
From Stereo 3D, Sensei?
Yeah, but in Stereo 3D, how Stereo 3D calculate this one? M1.
I'm not sure,
Sensei.
It's just a steel beam, right?
Yes.
I-shape. Technical manual of Stereo 3D. Could you search beam? Maybe much. Could you not here? Could you go down? Go down.
It's falling.
No, not yet. It's not yet. Could you go down. Not yet. No. Continue. Stop. Let's see.
Beam.
But it's a concrete. Could you go down? Go down. Oh yeah, this is steel beam. Could you go down? Yeah. Or maybe this one. With the moment. Yeah. So don't believe the value of Stella 3D.
Okay.
And you should check. And you know why? What I mean, at the moment of MY, all section is yielding. So all steel in this element each sigma y. Okay, then you can calculate this yielding moment. And please also understand the meaning of this equation.
Okay, sensei.
Okay, so Saro-san, do you have anything you want to show me? Saro-san.
Yes, I have. Did you sing? Okay.
Okay.
And I'm gonna talk about applications of solid viscoelastic coupling dampers in wind and earthquake sensitive tall beams.
Okay.
Its researcher is Michel Montgomery, Luz Ardila, and Constant Christopoulos. An introduction is what is a solid viscoelastic coupling? It is provide distributed damping that improves the dynamic performance of tall buildings for and quick for all amplitudes of vibration. From this picture, we can get damped structures amplitude is larger than damped structure. And this research has been going on at the University of Toronto in collaboration with the Nippon Steel Engineering, 3M, and the Kinetica for 20 years. And next, I'm gonna talk about impact studies on building this. In here, 3 examples. Example on building that we see this. First one is 6 stories and wind sensitive building. It is located in Toronto. Reason is this building is slenderest building, and second and third building is located in Southeast Asia, and building is based for tower seismic and wind critical development. Reason is located in of the world with the sum of largest wind and the seismic hazard. And third one is building is one of the most extreme seismic zone in the world, and it has the outrigger system. Now I want to talk about viscoelastic coupling dampers. Wheel dampers are typically configured in brace or wall panel configuration to capture racking deformation in low to mid-rise frame buildings. These tall RC buildings have a dominating cantilever flexural deformation under lateral loads, so dampers activated by interstory shear deformation, such as brace or wall panel designs, are less effective. And from this picture, we can see the viscoelastic material layers. This is viscoelastic material sandwiched between the and the bonded to multiple steel plates. This with each layer extending out and anchored into the vertically expanding structural members. From A and B picture, we can see the RC wall rotate and an actual deformation causing the solid rear material to deform in shear, like here. This picture, we can see this shear deformations acting on the solid material result in the instantaneous velocity depends on force and providing visuals dumping to the building as well as an instantaneous displacement depending elastic restoring force coupling the interconnecting elements during the dynamic response. And I'm gonna. The next one is full scale test. From this picture, I understand that viscoelastic layers has solid viscoelastic layers of in here, and from this picture above the full scale, we see this tested an actual frequency of 0.50 Hz or 3 amplitudes of this is, as can be seen in this result, the backbone viscoelastic history essentially the same from the 0.003 millimeter to 9 millimeter displacement through the dampers. Okay, and the solid model. It is consists of this and dashboard in parallel. It can be used to describe the dynamic viscoelastic material could carry at different frequencies of vibration. It is the spring and And from this, we can understand that viscoelastic materials force. U is the shear formation. V is velocity. K is stiffness, and C is the damping coefficient. And from this we find the force of the viscoelastic material. Then this is tested in shear. From this picture, start from a it shows a picture of full-scale VCTS test whereby from 2 to 1,000 kilonewton actuator arranged horizontally push the precast in here as concrete the panel cause information in the VCTS ensured configuration. For the B, the VCT undergoing shear deformation in the racking configuration, like in here. And how about for about C, in it dampers by 3 actuator capable of achieving a maximum load is 4,000 kilonewton, maximum peak velocity of 1,000 millimeter per second. From this picture, we can understand the left side 2,000 kilonewton actuator, and from right side double 1,000 kilonewton actuator push for this mid viscoelastic dampers. And from this fifth floor and the over bottom of the viscoelastic coupling damper is fixed to the floor, and over in here is swayed in two direction. Coupling beam configuration and outrigger configuration. For coupling beam configuration is coupling beams are commonly used to couple structural walls and increasing the stiffness of lateral load resistance system under large seismic loads, provided stable energy dissipations. We see this replace coupling beams with a gap between the slab and the VCTs to accommodate movement.
Where is the gap in this picture? Where is the gap? Coupling beams with a gap between the slab viscous damper. Where is the gap in this picture?
Okay.
Maybe here? I mean, slab and coupling beam with damper is a little bit separated. This is a gap, maybe. Maybe. Okay.
And above the outrigger configuration, highly This is highly effective for wind application as it reduces the overturning moment and during drifts. In seismic application, this system can reduce the drifts and overturning moment, but increases core wall shear and requires careful detailing in the outrigger level.
Okay.
And NVDs are used in outrigger by extending of the reinforced concrete walls and attaching with it on the outrigger to the external wall columns. Okay, and from before I show the three examples of tree building. Now I'm gonna talk about these buildings. First one is the 66-story building in the Toronto. It have the total 42 were used on from the 21 to 40 level of the structure. From this C picture, story drift, and without the undumped line is like in here 21 level to 40 level. In this section, undumped what can I say?
Story drift.
Yeah, story drift is more. We see these buildings, this dumped story drift efficiently.
I understand. Yeah.
Yeah, and this is reduce the story drift and the acceleration. And it was integrated within the structure and resulted in additional 5,000 square feet of usable penthouse real estate, as well as the fact that there were no requirements for tuning, monitoring, or maintenance with the VCD system. For about best 4 tower seismic and wind critical development buildings. And these towers were sensitive to both wind and earthquake loads because their interprofiles. From this picture, inter-story drift ratio for one in 50 years. It was limited wind drift as the original conventional design of each of the 4 towers existed. Prescribed.
What is the meaning of this?
Meaning?
Meaning 1 to 50 years. What does it mean?
And this is windstorm, like
windstorm.
Windstorm. Storms
Not earthquake. Before, I mean, what this year?
Yeah.
It is a, I don't know meaning of this 1 to 50 years.
This is windstorms. One in digital, like.
Windstorm. You are talking about wind.
Yes.
During 50 years?
Yes.
Really?
I guess, but I'm not sure.
Yeah, I thought this is sometime in earthquake design we consider in 50 years. So, no, 10% in 50 years. I don't know. This is so you are talking about wind. But it says seismic also. No, okay, it's okay. Yeah, please continue.
And it results that it is most syllable space for the client because it is required the little of flag wall and had no requirements to the inspect the tempers or maintain them over. Okay.
That's all?
Yes.
Yeah, you.
From this picture, we can understand that the liner is the one is the without viscoelastic coupling dampers, and with CDs is efficiently used it. Yeah. And next, for about mega critical building, it is consists of mega frame, and the belt. And it is distributed damping amounted to about 8% at the distributed damping for sway direction, and significantly more for the high modes. And this is to reduce the dynamic wind response by the more than 50% compared to the undamped build. And this picture, changing in the maximum values of peak response indicator of the VCD building along the X and Y direction compared to conventional building in indicated bubble. Y direction is peak inter-story drift ratio and the peak solution profile are plotted in this picture. This one is inter-story drift ratio, and the bottom of the peak floor acceleration profiles. As can be seen in these pictures, incorporation of the VCDs in design leads to significant reduction in the inter-story drift ratio and the floor acceleration throughout the height of the building. For example, maximum value of the peak in the storage from y direction are reduced by 21% under the SLA and 23% under the DA and 15% under the MCE level ground when compared with the conventional building. SLE's meaning is survive level earthquake. It's ground shaking without the damage. D is design level earthquake. It is damage. It is ground shaking with the damage but without the causing extensive loss of life. MCE is with the collapse, but potentially with the extremely damage. MCE. From this slide, we can understand cost reduction and the recovery time. Figure 15. Conventional structure and the VCT's difference in showed us, and we see this reduce the cost of cost reduction. Reduce the cost reduction is the main. And figure 16, from this, it is save the time of recovery of the building. And in this is Megatall's performance improvements for the VCT's structural and substantial. This is benefit in the net cost reduction estimated $20 million, and they save the 6 months in construction time were also estimated by the design team. This is to reduce construction complexity reduction of 3,000 tons of steel, 500 tons and 15,000 meter cube rate, and the reduction 3 meters in the foundation slab thickness. Finally, it is conclusion. The viscoelastic coupling damper use and configuration with coupling beam and the off-pressure system for both wind and the seismic performance enhancement. For above, we see this replaced a number of RC core beams in order to increase the level of inherent damping for wind stability requirements. It all allowed to maximum revenue on the project and eliminated the need for long-term maintenance and tuning or monitoring with the tuning system. Second, building one critical top wind and seismic performance-based design of port tower development. It were utilized in RCU flag wall configuration for enhanced wind and seismic performance. For about third building, it is increased the seismic performance of the building for all hazard level compared to the conventional structure, and its main among the RC coupling beam, and by replacing them with the high performing viscous coupling dampers. So structure also was the from this, and we see the structure also was estimated to the $20 million less expensive, and was estimated to reduce construction time by 6 months. That's all. Thank you.
Okay. So, here's some application example of viscoelastic damper. So could you study also some theory behind? Theory, equations, and also please try to apply Stella 3D.
Okay.
Okay. Just review is not research. You must do some analysis.
Mm-hmm.
Okay.
Okay.
Okay, so who is next? Ataya-san, you're next?
Yes. Okay. Since I prepared the runtime story and also distribution.
Yeah.
But when I apply for this landmass model, it doesn't work. But it don't move.
Why?
I don't know, Sensei. I think the points don't have problem because I applied in brain model.
Small, maybe, no?
No, it's wrong. I think okay.
Oh, okay. Oh.
When I extracted the output, all the max displacements are zero. It doesn't add on the model. I don't know.
Maybe this is because this is ramped math model?
Maybe in the past, did you apply rent on the landmass model or not?
How about the ordinary frame?
On the frame model it works.
In case of frame model, it works.
Yes, okay.
but Lamp-Thickness model, it doesn't work. なんだろうな。Sorry.
For example, it's just a model. It works.
Oh, okay. Okay, I will therapy.
Thank you.
Okay. Lamp-Thickness model. Okay.
But it's just a theory data input. It has to work. I don't know. The files are the same. They are just some numbers.
Okay. Okay, I'll check with the program. Yeah.
Thank you.
Any other people who want to talk today?
Sensei, I can.
Yeah. Okay, Sanayan-san.
Yes. So is my screen visible, Sensei?
Yeah.
So last which problem we were talking about, I actually found that the residual displacement is not there in the structure with the base isolation. That was coming due to large time step. If I reduce time step by increasing number of divisions, residual displacement is now gone.
Oh.
So it is coming back to its original position.
Oh, okay.
So since now I have finalized the tweaks that I will take, and I have designed my isolation system considering 6 seconds isolation time period. These are the isolators. So as I was discussing last day, that I have used 4 single isolators at the corners and 6 double. And similarly for the TMD, if it is tuned to the second stiffness, these are the parameters. And if it is tuned to the first stiffness, these are the parameters. So first hybrid design would be the TMD at the base floor with the second stiffness tuned to the seventh stiffness. And the second design was with the first stiffness tuned to the first stiffness, but TMD is in the base floor itself. And there I have found the base displacement in different earthquakes. And as expected, the base displacement is reduced by the first design, and it is increased the second design, where the TMD is tuned to the first stiffness. So these are the results summarized. Where there is overall 13% reduction in the maximum displacement of the base floor, and however there is a 30% detune increase in the maximum displacement by tuning it to the first stiffness. And now I am seeing the results on wind loading also. But since in case of wind loading, I am facing one small problem, that is because in the base floor, these are not isolated, these columns and these ones. So when I apply the load, these columns tend to stick to the ground, and because the isolators here have a lateral stiffness of almost zero, so their vertical stiffness is also not very high, and hence this tend to go up. The building tends to go up. but here they are causing some problem. So sometimes I get NaN values due to this error. So increase the vertical stiffness to the maximum limit for the free sliding isolators, and it is getting solved, but still for one or two cases, and maybe if I divide the time steps further, maybe this numerical error could be solved. But this is one problem which is occurring in the so from the few like from only in one or two cases it is not giving otherwise
I have one suggestion.
Yes, sensei.
So in the basement,
Yes, sensei.
I mean, you assume 2D rigid.
Yes, sensei, we can do that. I was also thinking about that.
You can put 3D rigid for this.
Okay, yes, sensei. Then we can do that. Then the whole slab will move together.
No. Even vertically, it moves together.
Yes, sensei. Okay, sensei, I will try with that. So from the preliminary results for the wind, as expected, when it is tuned to the first stiffness, for the wind, I am actually checking the response because the displacement response is very less. It does not matter so much, the base displacement, but the acceleration response will be close to the uncontrolled acceleration, because here the uncontrolled is not even visible. It is less than the orange one. One is the base isolator. So when I apply the TMD with tune to the second stiffness, the acceleration reduced slightly, but it is not reduced always. It is even same for the other direction. But when I tune it to the first stiffness, as the expected response is reduced much, and now I want to, like in the paper when we write it, I want to basis of some serviceability limit states under wind load. So now I have I have already used this reference for earthquake cases as well. So here we have some values of peak acceleration where it corresponds to the comfort limit of the air. So earlier, so if it is more than 15%, it is actually intolerable to the inhabitants, and these are the different limits. So I wanted to place the acceleration values within these limits, so that I could show that by using the first stiffness TMD, actually I could make it say not perceptible or just perceptible under the windstorm, and not annoying or very annoying or intolerable. So this is what to propose in the paper, and then I think now I will be able to. I am also working on the third design, which MD will be at the top, and the fourth design where there will be two TMDs, one at the top, one at the bottom, with stiffness one tuned to the first, second one tuned. So with these, I think I can finalize the results and I can write the manuscript.
So you put the two TMDs, one is for wind.
Yes, sensei. That is, I am hoping that would give me the best result. So I will have to check that.
Interesting.
Yes.
Good, very good. I've never seen this criteria.
Yes, sensei.
Copy of this paper?
Yes, sensei. I will send you this paper.
Okay, thank you.
You can check. Yes, sensei.
Okay, any other people who want to talk today? 吉江くんなんかつながってるけど、吉江くんなんかあんの？
前回同化したの時時間がなかったので。
じゃあ、浜くんもなんかあるってこと？吉江くんだけ。
はい、吉江くんの方です。
じゃあ吉江くんどうぞ。
はい、わかりました。
吉江くんに、来週の月曜日に建設生産工学の、TA をお願いしてるんだけど、 教室に持っていくさ、なんだっけ、ケーブルだとか、マイクだとか、だとか、教務課からもらうんだけど、やったことある？
ないです、まだ。
ない？教務課に行くと、部屋番号小さい入れ物っていうのかな、ポストみたいなのがあって、そこに入ってる、プロジェクターだとか、一式ね、持ってかなきゃいけないんだよ。授業の前に。うん。で、終わった後は、それを戻すんだけど、まあ、事務の人が全部こう、アルコール消毒してくれるので、自分で元のさずに、事務の方に入って言ってカゴ持って渡すんだけど、真島くんやったことあるよね。俺ね、月曜日、大学に、出張でいないので、まあでも、あれか、行けば分かっ
多分言ったらくれると思いますけど。
言ったらくれる。分かった分かった。じゃあ、とにかく部屋に行く前に教務課によって、この辺りか、よって、この部屋で講義するので、必要なものくださいって言ってね。
はい、わかりました。
じゃあどうぞ、全部始めてください。
前回の続きというか、建屋にかかる力っていうのをもう一回再計算したので、もう一回報告できたらと思います。2年、4年、6年で、ダンパーの音を示しまして、そこからトラス軸力による建屋にかかる力の今回求めまして、1年、2年、4年、6年の時 0.7、1.55、2.1となりまして、その反力的に考えたときに、0.68、0.17、1.5ぐらいになるっていう話だったんですけども、今回縮張力を考慮して建屋にかかる力っていうのを再計算しまして、で、縮中力に応じて滑車間にかかる力が働くので、建屋にかかる力 FV、延長高校と、ダンパ力級と初期張力 F を用いて、このように表すことができるとしまして、初期張力、統一で 0.5kN ニュートンとしたとき、建屋にかかる力っていうのが、最大6連の時で試したときに、水平方向に3、電池方向に、まあ大体 1kN ぐらいってのが分かりました。ここだけですね。
で、これが、タイムが結構大きな力なのかっていうのを、どうやって判断っていうかな。
これって先端が針の、垂直方向の力が針の先端より低かったら大丈夫ってことですか？それともモーメントで？
だから、その針にどう止めるかなんだけどさ、針がまあ、エッジ型こうだとすると、上下にこうフランジがついてるじゃない？だから、まあでも先端だろうな、きっとな。例えばもう接着剤でいいってなったらさ、接着面の面積で、この、引っ張りワイヤーの、今延直と水平に分けてるけど、まあ延直か。まあ延直でも、だから、接着面にかかる先端力と引っ張り力を今計算してる感じだな。だからそれを面積で割れば応力になるので、だから普通の接着剤でそれがさ持つよっていうか、これくらいの接着面積にすれば持つよっていうのか、で針自体は断面で割れば先端応力が出るんだけど、許容力度っていうのが法律で決まってるから、でも先端の許容力度ってあれかな、 通の幸福体力と同じ。僕、ちょっと、高構造の先端応力度ってよくわかんないんだけどさ。
はい、後で教科書見直します。
教科書に書いてると思うけど、で、長期の許容力度を下回ってれば、っていうか、まあ、それに対してね、1割増しぐらいで済むんだったら、すでに安全に作ってる針なので、1割増しぐらいは多分余裕だよな。
はい。
まあ、その何割増しぐらいになるかっていう話を、あと、じゃあどうくっつけるかっていう話で、接着剤でくっつくのか、ボルトだって楽勝だと思うけどね。
そうです。
うん。っていう話かな。
わかりました。
はい、はい。うん、これはこれで、まあ、設計者やりたがらなくても、技術としてはできる話なので、
そうですね。
これはこれで論文になるっていうか、結構いいかな。はい。じゃあ、了解です。はい。Okay, so shall we discuss the next meeting? And today is 8. 文化センター、世界に、16日、ラッキーミーティングでして、How about Friday? 3:16.
大丈夫です。
大丈夫 Is it okay? 16, 3 o'clock. Are you okay?
OK 先生。はい、大丈夫です。
はい。サラヤンさん。
Yes, it is fine.
Okay? OK. じゃあ、終わりますか。
OK。先生。
はい。
前回、なんか研究レポみたいな感じのことをおっしゃってたじゃないですか。東北の方で調べてるんですけど、向こうで会う予定の先生のスケジュールはありそうですか？それが決まれば、それに合わせてあと予定組めば。
今、イントロを考えてるの？
横谷君も声かけて、横谷君間の授業があるので、月火水のうち、月火水のどこかで。4月の10、11、12うちの2日か、17、18、19のうちの2日で考えてるんですけど。
いいよ。じゃあそのあたりで、でもたくさん知ってる先生いるからな。誰かは、はい、入ってんじゃね。なんか、7月の18、19。はい。今、はいはいはい。
まあ、1泊2日でいいかなと思う。1日目移動して、午前中移動して、1日目の午後か2日目の午前で、その先生方の都合、打ち合わせみたいな感じの都合で、あとは、なんか、石巻にある、地震のメモリアルセンターみたいなところと、あと、ハイエーバーなんですけど、津波の避難タワー、どんな感じなのか見てみたい。
そう。陸前高田にもすごくいいのがあるんだけど。
あれ陸前高田ってめちゃくちゃ遠くないですか？
うん。
そうですよね。
この間、天皇が、皇后がさ、訪問した、奇跡の一本松っていうのがあるさ、
はい。
施設としてはね、素晴らしい。
僕も建物綺麗なって思ったんですけど、いいなって
大変。まあ、レンタカー借りていかないと、電車も走ってないかな、近くは。
そうですよね。
まあ、石巻でもいいか。確かにね。
あと、原子力発電所の、なんていうんですか、災害伝承館みたいなところもあったんですけど、そこも遠くて、全部がバラバラにあるんで、どうしようかなって。
東北大学に行ったら、
はい。
なんだろうな。
地震研究所。
なんて名前だっけ？
国際。
そう。
はい、わかります。
まあ、そのこと自体が免震構造なんだけど、
災害科学国際研究所。
そう、災害科学国際研究所。そこに、佐藤武史っていうね、先生がいるの。
佐藤先生です。
もう教授になってると、彼、豊橋技術科学大学出身なんだよ。
佐藤先生がいっぱいいました。
佐藤健って書いて。
わかりました。
で、彼だったら自分の母校の学生だし、
なるほど。
粗末に扱わないと思うので、武史にちょっと相談するか。
はい。
施設の案内と簡単な講義とディスカッションをちょっとお願いできないかっていうことにしようか。
振動体もあるみたいなんで、なんかどんな研究してるのか。
別の先生かな。でも、伊香子先生って、伊香子先生は、この災害国際研究所だっけかな。
伊香子ってどういう感じですか
？50の子供。
いらっしゃいます。
いる？はい。伊香子先生もめちゃくちゃ、今度トルコに一緒に調査に行くんだけど、伊香子先生が、まさに精神ダンパー、ほら、回転減衰の本書いてるじゃん、教授。
あの先生ですか。
だから、真島君は伊香子先生とちょっと、話をすると盛り上がるかもしれない。
この完成コマ。
じゃあ、ちょっと行くメンバーと今の希望、分かったんだけど、あと、メンバーの名前も入れて、ちょっと概要ちょうだい、メールで。
どこまで指す？今のところ、前回先生がおっしゃってたシャライナとテシングと僕と横谷君。
4人ね。
入れてるんですけど、どうしましょう。他の理学生部ですか？博士の。
だって、旅費が出せないもん。
自腹だからっていけるってことです。
自腹だってもちろん行ってくださいって感じだよね。だから他の人自腹で行きたいって言うんだったら、行ってもいいけど、でもなんか自腹で行かせるのかわいそうだな。あれだけど、ちょっとね。
テシングは自分の研究費があるんですか？先生が出されてる。テシングです。
ブータンの彼はJICA が出してくれるよ。
なるほど。他JICAはいない。
さんも出してくれるかな。
エディソンはもう前行ったんで、もういいかなと思ってるんですけど。
そう、エディソンはね、トルコの今回の旅行で使い切ってるから。
なるほど。じゃあもうないってことです。
もうないの。残ってない。っていう感じ。だから、行ってきた？
はい、いました。
はい。じゃあ、俺の方から言うか。何時間ぐらい東北大で、だから他にも行くんでしょ？
でも、1日目か2日目のそんなずっと迷惑です。1日目の午後か2日目の午前のどっちかをこの先生方の都合に合わせて、その空いてる方で行こうと思ってるんで、
1日目の午
後か2日目の午前
のか2日目の午前で、2時間程度。
2時間、はい。
で、7月10日から10日。で、17、さっき休みの日じゃなかった。
17祝日なんで、この場合だと18の、午前か、18、10。 カースっていう。
はい。はい。じゃあね、佐藤武史君に話を伝えて、詳細は真島君と直接メールでやり取りしてくれって言うかな。いいそれでも。
はい、わかりました。
じゃあ、了解。伝えておきます。
はい、お願いします。
はい、はい。OK. So, see you, everybody. Bye-bye.
大変。